co-authors wanted to avoid the word monoid and semigroup in the title because they're both semigroup theorists and they think that everyone's biased against them. So my co-authors on this project are Stuart Margolis from Bar-Ilan University and Benjamin Steinberg from City College of New York. So the thing I want to tell you about today is this beautiful interplay between certain algebraic invariants of monoids and combinatorial topology of posets. And the talk will roughly go as follows. I'll tell you what these monoids are. I'll then describe what the algebraic invariants are. And then I'll explain how you can use combinatorial topology of posets to compute those. So we're going to start off with a hyperplane arrangement. And so we've already seen a few talks about hyperplane arrangements. And what we're going to notice is that a hyperplane arrangement embedded in a real space dissects our space into sets that we call chambers. So you just take the orthogonal complement of, not the orthogonal complement, but the complement of the hyperplanes. And so we get these connected components. Each of these is called a chamber. So here we go, we have 6 chambers. Some people call these regions. So each of these chambers is a polyhedral cone. So as a polyhedron, they contain faces. And these will be the faces of our arrangement. So for example, this triangular wedge here has 4 faces, the chamber itself, and it also has the 2 sides, as well as the origin. Okay, so we have all of these rays are part of our set of faces, as well as the origin. So here we have 13 faces, 6 chambers, 6 rays, and 1 origin. Any questions about the definition? Good. So we can endow this set of faces with a product structure. And the product of 2 faces x and y is the face that we first encounter after we move a small positive distance along the line from x towards y. So here are 2 faces x and y. We pick a point. We pick a point in each space, in each face, and then we move a small positive distance from x towards y. So we do that, and then we're in this new face, which is the chamber xy. Okay? So there's a few things we can notice about this product. One is that it's not commutative. So y times x will be this chamber here. Something else we might notice is that if you multiply a face with itself, you get itself. So every face satisfies the equation x squared equals x. So every element satisfies this equation. And then there's another identity which is crucial here, that's that x equals xy. So this means that if we start from x, we move towards y a bit, and then we change our boundaries and we want to go back towards x, well, we can't do that. We're stuck in xy. Okay?
So there's another
So
question.
Yes.
you have to pick a point that is not also a point, because of course it could have taken the origin. And then this.
So there's something I'm glossing over, and that's that each of these faces, we actually get a partition of the vector space, so each one is a relatively open set. You can just talk about like interior points, for example. That's another way around it.
And then the paths are short, these paths, so to speak, because you could also go the other way, from x to y.
Well, we're going along a straight line.
Straight line.
Yeah, so we're going along a straight line.
So which this one is not.
That looks straight to me. So from here to here, that's just go straight. I mean, it might be, and I guess I can make a little model. I think we had a question there.
So, I mean, is this algebra associative? Because
It's not obvious at all from this definition that it is an associative product, but it is.
And the same question.
Same question. If you're familiar with oriented matroids, you write down the covectors associated here, and you can actually describe the product in that case, and it just works. So trust me on that. Yes?
So if x is maximal, then xy will equal x, right?
So if we take a chamber, the chamber times anything is the chamber.
Right.
Because we take a point in here, we move a small positive distance in any direction, you're inside there. Yeah. Exactly. All right. I think we're good? Excellent. So a semigroup that satisfies these two identities is called the left regular band. So LRB for short. And I'm going to use the letter B for band throughout this talk here. And so these are the two identities we're interested in. Informally, what these identities are saying is that we should just ignore repetitions. So just ignore repetitions. There's various ways to interpret this, and you can come up with novel stories. But the point is, once you've included an element in your product, you no longer need to consider that anymore. So part of the original motivation to study these, or at least some of the more recent original motivation to study these, is that it provides a unified framework to study a certain class of random walks. So there's a theory of random walks on the chambers of an arrangement, and these include various different kinds of shuffling of decks of cards. Maybe I'll say a little bit more about that later. So here's a couple more examples. So first is the free left regular band. So we start off with a set. We're going to take all the words on our set, except we don't care about repetitions. There are no repetitions, so we're looking at only repetition-free words. And our product is going to be concatenation, except that concatenation might introduce a repetition, so we have to remove a repetition and a repetition. So if we multiply this word here by C, we concatenate and delete any later occurrences of the letter C. So this actually allows us to model a certain random process, which is referred to often as the set-in library, or the move to front rule, or the random to top rule. The idea is the following. You imagine we have a bookshelf. So we have all our books on one long shelf, and we decide to organize our book using this rule. Whenever we take out a book, we put it back at the front. And so this just corresponds to then, I'm going to use my book C, and then I'm going to put it at the front, so it's just a question of multiplying by a generator. And the long-term behavior of this, of this process is that my most favorite books will be at the front, and my least favorite books will be at the other end. Now we could tweak this a bit. We'll start with the graph, and we'll look at the free left regular band on the vertices, together with certain commutations. So we're going to introduce some commutations. We'll say some of the generators are allowed to commute. So two generators commute if and only if there's an edge in the graph that connects them. So some of you will quickly recognize this as the left regular band version of free partially commutative monoids introduced by Cartier and Fouata. And there's a nice random walk that you can define in this world too. It was analyzed by Athanasiadis and Diaconis, although they did it using a different left regular band, actually the one that comes from a graphical arrangement associated with the graph. All right, let's do an example of this. So here's a graph. We have one element is the empty word, because we have a monoid. We have the letters. These are the words of length 1. Here's a few words of length 2. These are the ones that correspond to the edges. These commute, so we can go back and forth here. Here's other words of length 2. The letters here do not commute. And then here's the words of length 3, the words of length 4. So we tally all this up, and we find 25 elements. Then we think to ourselves, that's 4 factorial plus 1. And so we make a conjecture. So this is the n factorial plus 1 conjecture. And that's this. If you take the cycle graph, so n nodes, and you look at the free partially commutative left regular band generated by this graph, its cardinality is n factorial plus 1. So you might quickly do a computation in your head, and you might complain. So the first thing you should do is you should assume that n is greater than or equal to 4. If it fails, or n equals 3. But then you could do, what did we say yesterday? We said we could just put it in a computer, and then we could just test this. And you can actually test this quite far using various techniques. I think you can verify this pretty easily up until n equals 11 or n equals 12. Challenge to go further. Challenge, prove it. So if you're bored in the rest of the talk, here's a nice challenge. I'd like a bijective proof, by the way. Other examples of left regular bands. So as I alluded to before, the covectors of an oriented matroid possess a left regular band structure. Complex hyperplane arrangements, there's a notion of faces in this world too, and this also admits a left regular band structure. Hugh Thomas and I, we took these previous examples and we tried to give a definition of oriented interval greedoids that kind of abstract some of the properties we see there. And we really took the point of view of left regular bands as well. This is a recent example. The faces of a CAD0 cube complex also give you a left regular band. So what's a CAD0 cube complex? So first, what's a cube complex? A simplicial complex, you glue together simplices. So for a cube complex, you group together cubes. CAD0 means you want to glue them together so that your space is simply connected and negatively curved. Okay. Well, you get some nice left regular bands as a result. If you start with any finite acyclic quiver and you look at its path algebra, then this actually turns out to be the algebra of a left regular band. So this class of semigroups is rich enough to actually say something. It's rich enough to actually encompass the class of hereditary algebras, for example. So they're not too complicated yet. It's a rich class of semigroups. And these things turn out to be everywhere in combinatorics. So Bidigar, Hamlin, and Rockmore, they're the ones who first looked at these random walks in hyperplane arrangement. The theory was later developed a bit by Valero, Brown, Diaconis. Ken Brown was the first one to look at this from the perspective of left regular bands. Various different random walks have been studied using this. And then since then, there's also been other combinatorial semigroups that have been considered. And these things include things like operators on linear extension of posets, parking functions. There's a nice parking function monoid that people really haven't looked at too much, and so on. So a lot of things. So the goal of our project is actually to understand extensions. So giving two modules for our semigroup, or for our monoid algebra, we want to understand the possible extensions of these modules. Now I know that this might not be something that's too familiar with this crowd, so let me describe what these are. The idea is that we want to answer a question which is very natural. Given two modules S and T, how can we combine them to form new modules? And so what we want is that we want a new module M, and we want S to be a submodule of M, and we want T to be the quotient of M by S. So this is something that's familiar to combinatorists, right? We have some objects, we want to combine them together to make new, interesting objects. I guess one case that's very familiar to everyone here is the case of for the symmetric group, and we look at modules for the symmetric group. When we're working over the complex numbers, there's actually only one way to construct an M like this, and that's to take the direct product, the direct sum. In general, the answers can be much more complicated and much more interesting. And it turns out that the right setting is to look at these things called short exact sequences. So here we have a sequence of a bunch of modules, ST, and we put M in the middle. And then we impose certain conditions. And the conditions you impose are exactly the conditions you need to get these two things. So we want S to be a submodule of M, and we want T to be a quotient of M. All right. Then, it turns out that this class is actually a bit too big, so we have to introduce an equivalence relation. And it actually admits a group structure, and in this way we actually get a vector space. So equivalence classes of these short exact sequences give you, or can be endowed with a vector space structure, and this is X1. So these are the first extensions. If you want to do n extensions, all you need to do is change this M here, you expand it by putting in more modules in there. Okay? But, I mean, the point here is that this is answering a very natural question. And we could do it using Poset topology. So here is an informal statement of the theorem, stated as a haiku. So, for a left regular band, well, sorry, that doesn't work. Sorry. For an LRB, the extensions are Poset cohomology. And that scans appropriate, that scans adequately. So I've told you what extensions are, I've told you what LRBs are, and I tell you what these posets are. So the first poset we look at is actually the monoid itself. So we take the monoid and we endow it with this relation. So we say that x is less than or equal to y if and only if y times x equals x. So this is the poset you get for the free left regular band on 3 elements. So just to convince ourselves, AB is less than A because A times A times B is equal to AB, due to the fact that A squared equals A. So this is a relation which is very natural from the point of view of semigroup theory, and also from the point of view of hyperplane arrangements. So for hyperplane arrangements, this corresponds to the face relation. X is less than or equal to y, if and only if y is the face of x. You turn things upside down. The other poset is this one here. These are the principal left ideals of our semigroup. So given an element x, we multiply it on the left by every element of the semigroup. And then we order this by inclusion. So for example, like this set here, BA, this is just saying these are all the words that contain an A. This is all the words that contain A and C, for example. And we order this by inclusion. Again, very natural from both perspectives, semigroup theory and hyperplane arrangements. For hyperplane arrangements, this corresponds to the intersection lattice. And something that's also really fantastic here is that this plays the role of the weight lattice for our semigroup. The elements here index or parameterize the simple modules of our group, of our semigroup. So this means that what we want to do is actually use, so when we want to talk about two simple modules, we're actually talking about two elements in this poset. And so that's what we're going to do now. We're going to take two elements here, and we're going to use them to carve out a subposet of this one. So what we do is we take the generators of each. So this left ideal is generated by B, and these are all the elements that generate this one here. So we take all the elements that are strictly less than little b, and weakly greater than one of the other ones here. Okay, so this is our subposet that we're interested in. Again, from the point of view of hyperplane arrangement, this corresponds to restriction and contraction of hyperplane arrangements. So these constructions are very natural from that point of view. And so here we get to a more precise statement of our theorem. So our main theorem says that if you want to compute extensions between two simple modules, you need to compute the Poset cohomology of certain posets. So first, as I said before, the simple modules are indexed by elements of this lattice. So given two elements here, we use that to carve out a subposet, and then we compute the Poset cohomology of this subposet. All right, so here delta is the order complex. So this is just the reduced cohomology of the order complex of this poset. So that's what I refer to, or everyone refers to as Poset cohomology. Notice there's a change in dimension. There's a degree shift. That's going to be important. So this is what establishes the interplay between some nice topology on one hand and some nice algebra on the other. And we'll see nice examples of this. Let's do a quick example. Here we're going to look at x1. So we know that if we want to compute x1, we're looking at the zeroth reduced cohomology. Even if you don't remember much from algebraic topology class, you should remember that this is just the number of connected components minus 1. And so this isn't too, so it's pretty easy to compute this. So here we go. We start with these two. We look at the the subposet here. We count the number of connected components, subtract 1, and we'll record this by an arrow. So this arrow here just says that dimension of x1 is 1. So number of connected components minus 1. So let's do it again for these two. So we compute our subposet. So here we end up with 3 connected components. And so we put in two arrows there. Okay? And we'll do one last example. We'll just use our definition. We take 2 representatives. We compute the subposet. Here there's only 1 connected component. That means we put no edges here. And you continue along these lines, and you get this nice, beautiful directed graph. And now, I've tricked you into computing the quiver of an algebra. So even if you don't know what a quiver is, you've now at least once in your life computed the quiver of an algebra. So the quiver is a directed graph whose vertices are simple modules, and the number of arrows between 2 simple modules is just the dimension of the first extension space. All right. Low degrees. So this is what we just did. We can use, so here's the application, some things we can do with this. So in low degrees, we can use this to compute the quiver. So we can use topology or topological aspects of these posets to give us information about the arrows in the quiver. Knowing about x2, we can deduce information about the quiver relations. And so this is just the reduced cohomology in degree 1. This actually leads to a topological characterization of left regular bands whose algebras are hereditary. This means that there are no quiver relations. And this kind of actually answered our main goal. Like when we started this project, we wanted to understand a particular theorem of Ken Brown about hereditary left regular bands. So this gives a nice conceptual setting to that. So these are the low degrees. In the opposite extreme, we can look at the maximal degree in which these extensions are non-vanishing, or in which the cohomology is non-vanishing. And so if we translate that into combinatorics, that's measured by something called the Lorentz number of a simplicial complex. So that's the maximal degree where subcomplexes have non-vanishing degree, non-vanishing cohomology. So this just gives us a straight upper bound. And so if we do this for the free partially commutative left regular band on a graph, so we've already defined these, then this global dimension here actually coincides with the Lorentz number of the clique complex of the graph. So this gives us a nice new interpretation of the Lorentz number of the clique complex of the graph in terms of non-commutative algebra. And this number here is also the Castelnuovo-Mumford regularity of the Stanley-Reisner ring of this clique complex. For some applications to hyperplane arrangements, if you take an EL labeling of this weight lattice, so the lattice of principal left ideals, then this actually can be used to write down an explicit eigenbasis for the transition matrix of the associated random walks. This is a nice application to one of the original motivations. This is actually something else that's a little bit surprising. So we started off with an example of a hyperplane arrangement which was central. So everything went through the origin. This meant that the semi-group we constructed was actually a monoid. It had an identity element. But if the arrangement is not central, it's not necessary that our semi-group is a monoid. Actually, in fact, if it's not central, it's not a monoid. There's no identity element. Yet, if we look at the semi-group algebra, it's unital. It still has an identity. So this was something that was overlooked by everyone else before. It seems like no one had seen this before. No one had noticed that the semi-group algebra actually gives you a unital algebra. And we found this in a very, very indirect way, because we computed a bunch of quivers and then noticed certain nice properties. For CAD0 cube complexes, this weight lattice, we can actually prove its Code-Macaulay, and we do it in a very unorthodox way, in that we compute these X spaces for the face monoid here, and we end up proving that it's an incidence algebra, we end up proving that it's Cazul dual, and that Cazul dual is the incidence algebra of this lattice, and that implies that you get a Code-Macaulay Poset. So I mean, this is a very indirect way of doing it. So here's another challenge. Prove that. All right, so I'll end my talk there.
Are there questions? Okay, before, there is a question.
So one thing, so you're doing it for faces of an arrangement. Can I do it for a fan? And if you can, then is the relationship work?
So I think the answer to the first part is yes. The answer to the second part is I'm not sure. That is something that's come up. And even this dimension shift in terms of X and the cohomology actually suggests that there should be something in that direction, but we haven't pursued it deep enough yet.
Okay.
But it does look like there's something along those
You can
lines.
do LRB for L.
You can define, yeah, you can
LRB
define,
for fans.
yes, yeah. We can discuss that a bit more.
So you've got this n factorial plus 1 conjecture for the
Yes.
LRB of a cycle. Are there other graphs which have either provably or conjecturally nice?
We looked at, we gave this kind of problem to some undergrads and certain families of graphs, and they were able to prove, like find nice formulas and prove certain things. But this is the one that we still don't know how to deal with. We didn't look too much. Like, I mean, I have some software, so if you could give me a family of graphs, we can run the numbers and see what happens. We can put it into the computer.
One more?
What do you know about buildings? Because quer dizer, o complexo special example.
So there's a lot of nice stuff that happens when you start talking about Coxeter complexes and so on. So if you look at a building, you can define a product, but in that case it's not associative. So the product is not associative, but you still do a lot of nice things there. So Swapnil Mahajan has done some stuff in that direction. And yeah, there's a lot of nice stuff you can say in that direction too.